Hello, good day everyone. This is me, your instructor again for this subject, Foundation Engineering. And today we are going to discuss the stress distribution in soils due to line and strip loads. Actually, this is just a continuation of our previous lecture regarding the stress distribution in soils due to point or concentrated loads. And to start with, we have this first, the line load. So based on the illustration, the basic equation used for computing the vertical stress at any point P in an elastic semi-infinite mass is of Boston's formula. And by applying the principle of his theory, the stresses at any point in the mass, due to a line load here, where this is Q over unit length of infinite extent acting at the surface may be obtained. So the state of stress encountered in this case is that of a plane strain condition actually. So the strain at any point P in the y direction here, which is parallel now to the line load, is assumed equal now to 0. And the stress, the sigma y, since this is our y direction, the sigma y here, which is acting normal or perpendicular to this x and z plane, is the same at all sections, and the shear stresses on these sections are equal to 0, and this is according now to the plane strain condition. So we have now this distance x, the horizontal distance x, we also call this one as the radial distance, from the vertical axis z, and we have now this depth of z here, and we have now this point P acting at a certain distance, with this r at an angle theta from the vertical z-axis. So if we get now the value of our r, it is just the sum, the square root of the sum of the squares of our x squared here and the z squared. And if we are going to determine now the theta here, is just we use the cosine theta, which is the z over the square root of the sum of squares of the x and the z. Okay, so by formula, the vertical stress is just equal now to this uniform pressure small q over the z times this quantity 2 over pi over 1 plus x over z raised to the squared quantity raised to the power of 2. So if you can remember from the point load, the distance there was denoted by this r. Okay, but in this line load, our horizontal distance is just denoted by this variable x, and our r is just the resultant, of this x and of this z value. Okay, so that's why here we use now this x, which is the our horizontal distance, from this vertical z-axis. And then if we denote this 2 over pi all over this 1 plus x over z squared raised to the power of 2 equal now to this influence factor z. So this equation reduces to this q over z times this influence factor I subscript z. And the I subscript z is the influence factor equal to 0.637 at this ratio of x over z is equal to 0. Okay, so as you can still remember that the stress is maximum directly below the load. So in this case, uh, it is maximum actually directly below this line load here. Okay, so proceeding, we have now this strip load. And the state of stress encountered in this case also is that of a plane strain condition, as for the line load. And such conditions are found for structures extended very much in one direction, especially in this y direction, and such as strip and wall foundations, foundation of retaining walls, embankments, dams, and among others. So in this case, no, we have now this strip footing. So we have now this differential strip, no, at a fixed width of b. So we have denoted this one as the differential dx, no, this differential dx, and we have now this load p acting at a distance x from the vertical axis z. Okay, so we have also now this q per unit area, and if we consider this one here at infinite length, no, of this strip footing, so it is just q over this infinite length. Okay, and for such structures, the distribution of stresses, no, in any section will be the same as in the neighboring section actually. So the same as that for the plane strain condition, no? Provided that the load does not change in direction, no? Especially if we are it is acting on the y direction here, so that the load does not change in direction perpendicular to the plane considered. Okay, so if the load change in direction, so that plane strain condition is not applicable here. Okay, so we have also now this strip load, no, from this at fixed width here, and we have the corresponding angle beta and this angle. Okay, so we will use these angles, no, in our formula actually, in our calculation, especially if we are going to use the graph. And for the vertical stress sigma z, this is just equal now to q, the uniform pressure q over pi times this quantity here. Okay, so take note that this inverse tangent of x over x minus b, this one, and this inverse tangent of z over x plus b here must be in radian unit. Okay, it is in radian. And for such point p here, if our x, this one, is equal to 0 to less than or equal to b over 2, where in this case this is now our fixed width of the footing, which is b. If our x is 0 or less than or equal to b over 2, so this inverse tangent of z over x minus b here becomes this pi plus the inverse tangent of this z over x minus b. Otherwise, we will use, no, this formula if it is not complying with this condition. Okay, so proceeding, we also have now this vertical stress formula for sigma z and sigma x, which is equal now to this q over pi times this quantity here, and for the sigma x is just the same, but it is just only a minus here. Okay, and for our principal stresses, sigma 1, sigma 3, so we have also these corresponding formulas, q over pi times beta plus sine beta, and for the sigma 3 is just the q over pi times beta minus this sine beta. So actually we have now this graph, no, in figure 3, which is non-dimensional values of the ratio of our vertical stress over the uniform pressure Q for strip load. So actually we can use this one, no, if you wanted to, but in our problem application we have just to calculate first. Okay, but you can use this one anytime. Okay, to get this ratio of sigma z over the q. Okay, so the non-dimensional values of this sigma z over the q are given graphically here, and this can be expressed in a more convenient form, no, as the formula we have discussed, no. And proceeding with our next slide, we have now the sample problem number 1. Okay, so 3 parallel strip footings, 3 meter wide each and 5 meters apart, center to center, Transmit contact pressures of 200, 150, and 100 kilopascal respectively, and calculate the vertical stress due to the combined loads beneath the centers of each footing at a depth of 3 meters below the base. And assume the footings are placed at a depth of 2 meters below the ground surface, and we are going to use the Bossinus method for these line loads. So as you can see in the figure, this one, we have this uniform pressure, no, for our first footing, no, at 200 kilopascal. For the second is 150, and for the third footing is just 100 kilopascal. So take note that the footings are placed at a depth of 2 meters. Actually, it would be from this until here, it is 2 meters depth. Okay, this 2 meters depth. And the same also for the footing, the second footing and the third. But in this case, we are going to neglect, no, the depth of footing. We are just only considering this depth of 3 meters below the base, no, which is, this is our base, so this is 3 meters. So we are going to calculate the stresses here at point A, point B, and point C. So take note, the footings were 5 meters apart, no, from each other. Okay, so proceeding, first we are going to calculate now the stress. Okay, the vertical stress at point A. Okay, so after this one, we are going to apply the formula for this stress. So actually, we have now this vertical stress of sigma z. Okay, sigma z is just equal to, we have now this uniform pressure q, small q, over the z. Okay, times this quantity, we have now this 2 over pi, okay, all over this 1 plus this x over z. Okay, squared, and we are going to raise now this to the power of 2. Okay, so this is now our basic formula for the vertical stress, sigma sub z, in which this is just equal now to our uniform pressure q over the z times this influence factor I sub z, where we denote this I sub z equal now to this quantity. Okay, so to start with the point A, so we are going to denote this one as sigma z, okay, at point A. Okay, so we have now, so if we are going to substitute this one, so our q is just equal now to, for point A, so we have 200. Okay, so we have 200, and our z is just equal now to 3 meters. Okay, so we are going to substitute the given values here. So this is 2 over pi, and then we have now here below 1 plus our x is just equal now to, since we are considering here, so our x here is just equal to 0, no? So since we are considering first the point A, so we use this one as our reference point. So our x here is just equal to 0 over 3 raised to the squared, and then to the power of 2, this one. Okay, and then after this one, for this point A, we have this first footing. Okay, so we are going to have this second footing here. Okay, this one, so we are adding plus, we have now this 150 over 3, okay, times this 2 over pi over this 1 plus, so what would be now our x? So from here as our reference, so its distance is 5 meters, so that is why it is 5 divided by z is 3, okay, squared, and we raise this one to the squared, okay, plus the last one is this third footing, okay, so we have now this 100 divided by 3 times this 2 over pi, and then we have this denominator of 1 plus our x here is just from here 5 and 5, so it is 10 meters, so 10 divided by 3 squared raised to the power of 2, and after calculating this one, we have now this value of our sigma z at point A is just equal to about 45 kilo Pascal. Okay, so we have now this vertical stress actually at point A equal now to this 45 kilo Pascal. Okay, so next is we are going to calculate now the vertical stress at considering this point B. Okay, so proceeding, this is now our point B, stresses at point B. So we have now this same formula again. We are just going to substitute now the values, no, using this sigma z at point B. Okay, so we have now this q over z. So our q here is, so we are now here at point B. So we are going to consider now this first footing. Okay, so our q is just equal to 200 divided by q over z times we have this 2 over pi over 1 plus our x here is just, since we are now at this point B, so its horizontal distance is 5 meters. Okay, so this is 5 divided by 3, okay, squared raised to the power of 2, okay, plus this putting here, so we have this 150 divided by 3, okay, and then we have now this 2 pi, 2 over pi rather, and then we have 1 plus our distance here is, we are now base our reference from this point B, so that is why our x here is just equal now to 0 over 3 squared raised now to the power of 2, and we have also this third footing which is 100 over 3 times this 2 over pi times this divided by rather this 1 plus, so from here to this third footing is horizontal distance is 5, so it is 5 divided by 3 squared raised to the power of 2. Okay, So calculating, so we have now our vertical stress sigma g considering point B is just equal now to about 36 kilo Pascal. Okay, so we are done with our vertical stress at point B. And proceeding with our stresses at point C, so we have now this calculation here. Stresses at point C. Okay, so again, we are just going to distribute and apply the given values from the sigma z at point C, which is just equal now to, so we are now here at this point C. So our Q, considering this one is 200 divided by Z is 3 times we have this 2 over pi, and then we have this 1 plus our x here is just from here is 5 and 5, so this is 10. 10 divided by 3 squared, okay, raised to the power of 2, and then plus this one we have 150, okay, 150 divided by 3 times again we have now this 2 over pi, and then 1 plus our distance from here to here is just only 5 meters. 5 divided by 3 squared raised to the power of 2, and then lastly we have now this here third 14, which is we have 100 divided by 3 times our 2 over pi, and then we have now this denominator of 1 plus our x here is just simply equal now to 0 divided by 3 squared raised to the power of 2. Okay, so actually here this is just 1, okay, so the square is 1, so 2 over pi divided by 1, so we are just it is just actually 100 times 2 all over the 3 pi. So calculating our sigma z at point C is just simply equal now to how much? Equal to 24 kilo Pascal. Okay, so this would be now our stresses, no? At point A, at point B, and at point C. So this is just a simple illustration on how we use now this formula, using the Boussinesq formula for line loads. Okay, so proceeding, we have now this another sample problem, no, for the strip load. So we are done with the line load. So here we are referring to this figure 2a, no, here for strip load, where our B here is just equal now to 4 meters, and our uniform pressure Q is just equal to 100 kilopascal, and for point P, this one or this one, our Z is just simply equal to 1 meter, so 1 meter rather, so 1 meter, and our X, this one is just simply equal now to again 1 meter. So we are going to determine the vertical stress at this point P. Okay, so for solution, we have now this simple calculation for this. Actually, we are going to check, no, if our x is less than or greater than our b over 2. So checking, so for checking here, So our x is just equal now to 1 meter, okay? And we are also given with our z, which is equal now also of 1 meter. So our b is also given. Actually, b is just equal now to how much? 4 meters, okay? So therefore, our b over 2 is just equal now to 2 meters. So x equal to 1 meter is just less than, okay? It's less than our b over 2, which is 2 meters, okay? So we can say that we need to, from the original equation, actually, from the original equation is we have this sigma z. From the original equation is we have this sigma z is equal now to our small q over this pi, okay? And then we have this tangent, the inverse tangent of our this one z over x minus our b. This is our original equation actually. And then we have now this minus inverse tangent of this z here, and then we have x plus our small b, and we also have this minus this quantity minus this one. We have here, we have 2bz times this x squared minus b squared minus our z squared here, okay, all over this quantity x squared minus b squared, and then plus this z squared raised now to the power of 2 plus this 4 b squared and this z squared, okay? Actually, we can use the value of our this value of capital B, you know, since our B is just simply equal now to 2 times this small b. So actually, you can replace the small b here with this capital B. But as of the moment, we are still using this equation, no? So accordingly, this is just good if our x is just equal or greater than this b over 2. But in this case, since this is less than, so according now to the principle is we are going to replace this one with this tangent, this inverse tangent of this z over x minus b. We are just going to replace this one with this pi, no, if you can still remember, pi plus this inverse tangent of this z over the x minus b. Okay, so from this original equation, this inverse tangent of this z over x minus b, we're just going to replace this one with this pi plus the inverse tangent of z over x minus b. So therefore, our sigma z is just simply equal now to this q over the pi times we have now this inverse tangent of your z over x minus b plus this pi, and then this minus the inverse tangent of your z over x plus b. Okay, and we have now this term minus this 2b z times this x squared minus b squared minus z squared all over this x squared minus b squared plus this z squared raised to the power of 2 plus this 4b squared and this z squared. Okay, so we are going to use now this formula actually to get now the value of our vertical stress. So proceeding, we have now this following calculation. So our sigma z is just equal to this q over pi times this one is in terms of this one, in terms of our capital B, this is just equal to B over 2. Okay, so our tangent, this would be now equal to tangent of the inverse tangent rather of your 1 over 1 minus 2. Okay, and this pi here plus pi, and then we have this minus inverse tangent of your this one z over x plus b. So in terms of capital B, this is just equal to b over 2. Okay, so this is just equal to 1 over 1 plus 2. Okay, and then we have now this quantity here minus okay, so we have here this quantity 2bz times this one all over this quantity here. Okay, so we have 2 times, we have now this 2 again times our z is 1, and then this quantity x squared minus b squared minus z squared. Okay, so we have here 1 squared minus 2 squared, and we have now also this 1 squared. Okay, and all over this quantity here. So first we have this 1 squared minus 2 squared, and then we have plus z squared is plus 1 squared. Okay, raised now to the power of 2, and we have here plus 4b squared z squared plus 4 times our b is 2 squared and our z is 1 squared. Okay, so we have now this value of our z sigma z then equal now to this q over pi times, so we have here this value in radians is just equal now to minus 0.785 radian plus this pi, okay, and minus this one, so it's equal now to 0.322 radian and minus the value of this quantity here. So this is just equal now to minus 16 over 20, or simplifying, we have now this vertical stress sigma z is equal now to q over pi times this minus 0.785 plus p minus 0.322 minus this one 0.8, okay, and then we have this value of our sigma subscript z here, which is then equal now to 0. Q over pi times the value of this one is just equal to, so by the way, actually here is actually this is from here minus this quantity, but this 16 over 20 is just negative here, okay, so this would become negative and positive, actually this would become plus actually, okay, so the result of this is negative 16 over 20, and since this is negative here, so this is becoming positive, okay. So proceeding with this one, we have now this the sum of this minus 0.785 plus pi, and then plus this negative 0.322 plus 0.8 is just equal now to this 2.8346, okay. So simplifying this one, we can get now, since our q is just equal now to 100 over this pi times this 2.8346, so we can calculate now the value of our sigma z, which is equal now to 90 kilopascal, okay. So this would be it no for this problem actually, in calculating now the vertical stress using now the Gaussian equation, no, for this strip load. So in this case, we have now this vertical stress sigma g equals to 90 kilopascal. So I think that would be it now for this problem, and also for this lecture today. And thank you very much everyone for listening and watching, and please these are now my references, no, with regards to this discussion, and please do not forget not to like, subscribe, and share for more updated videos regarding our subject, foundation engineering. And thank you very much once again for listening and watching, and God bless.